Hello, and welcome to Math in 50 CBE Review 3. I am Ryan Austin.
I'm India Evans.
We're going to be helping you guys review for the CBE 3. Just some things of clarification. This is being recorded, so we're not going to ask for any names. And if you do ask questions, we're just going to repeat them, just so that whoever is going to watch later, that they understand what's going on and they can hear the questions that are being asked. Sounds good? All right. So to start things off, CBE 3 covers lessons 11 through 16, and these include our quadratic functions, polynomials and their graphs, polynomial division, real zeros of a polynomial, the fundamental theorem of algebra, and rational functions and their graphs. So to start things off, let's go over quadratic functions and what those mean. So quadratic functions always have some x squared term in them, or when you factor them or do something to them, you'll get an x squared. For example, the function can be expressed in a lot of different ways. Right here we have our vertex form right here. I'm pretty sure this is our standard form. And what's that one? That's the factored form? Okay, I just needed a quick reminder. And the middle one right there is factored. And with each of those, there are two x values that when you combine them together, they are squared or they give us the vertex, and each one is unique and gives us some information that is useful to us. Okay. And we can always find the vertex and x and y intercepts using different methods with these forms. Sweet. So, let's do a little bit of practice. I guess, does anyone have any questions with quadratic functions and how we can find x and y intercepts or the vertex of those things? Is anyone feeling pretty good on that? All right. In that case, we can do some practice. So to start off, it is asking us to find the exact coordinates of the vertex and the x-intercepts for this parabola right here. Now, as you might have noticed right off the gate, this is in standard form, not in vertex form or in our factored form, which would be a little bit easier to find our x-intercepts and our vertex. However, there are still some tricks we can use to find the vertex and our x-intercepts for this. When we're in standard form, we can find our vertex by using this formula right here. And the b and the a's are referring to the values, the coefficients before our x squared and our x. So a pretty simple way for us to find the vertex of this parabola is by just plugging in these values. So for example, we'll have -4/3 over, if we multiply the two a, which our a in this case is 2/3, we will get 4/3 again. And then we plug in to the function f our -4/3 over 4/3. And as you might have noticed, -4/3 over 4/3, that's just -1. And if we plug in -1 into our function, it's going to equate to 1/6. Does anyone want me to kind of just quickly walk through that? Or
yeah.
Did
you do that?
Yeah, all good. So using this function right here to find the y coordinate for our vertex, we need to plug in -b over 2a into our parabola right up here. So let me quickly grab an eraser. I'm just going to quickly erase this to give me a little bit more room. So what we can do is we can plug in, oh, now it's black, cool, -1 into, for our x values of our parabola. And just as some context, that -1 is coming from us evaluating the -b over 2a that we were using before. Is everyone still following? Okay. So to evaluate this, -1 squared is just 1. So we'll be left with 2/3 right there. 4/3 times -1 is going to be -4/3, then plus 5/6. And then we can multiply both the top and the bottom of these fractions to get them all in the denominator 6, and then we can just add them together. So we would get 4/6 minus 8/6. Gosh, that's hard to say. Plus 5/6. And that will get us -4/6 plus 5/6, which is just 1/6, which is the y-coordinate of our vertex. Pretty cool. So that is how we find our vertex. And then to find the x and y intercepts for standard form, we can use the quadratic formula. Pretty standard right there. However, I need to erase this again. I keep on running out of room. So let's put together our quadratic formula and find our x-intercepts. So the quadratic formula will be -b, which in our case is 4/3, plus or minus square root of b squared minus 4ac all over 2a. And if we simplify this, we would get, nope. We'll get 16/9, now it's red again, minus, let's see here, I'm just doing some math in my head, that's going to be 40, 18 times 4, I can't do that math in my head very fast. What is 18 times 4? Can someone help me out with this? Oh wait, no, we don't multiply. I'm sorry, we don't actually multiply the denominator by the 4. And now it's black again. I don't know why it keeps on changing colors. Very frustrating, if you ask me. But if we keep on going, this is inside of our square root in front of the -4/3. Gosh, I am making a mess of this. And if you're looking closely, as we continue to simplify underneath the square root, we're going to get 32/18 minus 40/18, which is going to be -8/18, which, as we've learned from our previous CBEs and the previous things we've learned in this class, negatives inside of a square root will give us imaginary numbers. And if the inside of our square root is imaginary, that means our x-intercepts don't exist. So for this problem, our vertex is going to be -1, 1/6, like what we found before, but we do not have any x-intercepts. Any questions on that? Yes.
So when you just put D and E?
Would you put D and E for no x-intercepts? D and E works. You could just say there are no x-intercepts. You can just kind of say that works too. But yeah, yes, you have a question?
This is just a question about the entire problem set, okay?
Yeah.
When you're doing this, I saw that you could, when you got into the sixth, you could get the sixth as a denominator to find a common denominator.
Yes.
And then multiply it all by, say, 6 again to get rid of the fractions. Would that be okay, since it'll make it easier and you won't have to?
So I guess to make it simpler, just multiply 6 across all the denominators. The real question is, does that give you a different value for your vertex?
No,
if it doesn't, then that's okay. If you're making sure that you're keeping the, I guess, all the changes you're making inside of the function, and there's no numbers falling off into the void, that's okay. If the work is still getting you to the correct answer and all you're doing is just making it a little bit easier for you to just work with, that is okay. Just make sure that you're not adding, subtracting, multiplying, or dividing values that you don't then change back at the end. Sounds good? Okay. Any last questions with problem 1? Are we all feeling okay on this one? Oops. I don't know. That's fine. All right. So for problem 2, we're going to find an equation of a parabola that has the vertex at the point 3, 4 and contains the points 5, -1. This one is pretty straightforward because we can start by using the vertex form of our parabolas. Like here before, we have our vertex form. And what we can do is we can plug in the coordinates of our vertex into that to quickly find it. So using that vertex form, which for us was ax minus h squared plus k, we can plug in our vertex to find x minus 3 plus 4 is the first part. And then the last thing we need to find is this coefficient right at the front. And the easiest way to do that is by using the points that we've been given 5, -1. So what we can do is we can plug in 5 as our x, and then we can solve for -1. And as we do so, we can then find a, and that will be our parabola. So let's plug in 5 into our x. So we will get a 5 minus 3 squared plus 4. And then we simplify and solve this, we'll get -2. Nope, just 2, not -2. We'll get 2 squared plus 4. That'll leave us with 4a plus 4. And then what we can do is we can set this equal to -1 because that is our y value for that point. And then we just solve for a. So we can subtract 4 from both sides, leaving us with 4a equals -5. And then we can divide both sides by 4, giving us a is equal to -5 fourths. And so the equation of our parabola is going to be -5 fourths x minus 3 squared plus 4. And as you can see, that is our solution right down here. Any questions with any steps or decisions I took with that one? This one's pretty straightforward. You can just start by plugging in the points of the vertex 3, 4, and then you just solve for a. Nice and straightforward that one is. All right, and then this is the second part of this question where it's asking us for the y coordinate of the point where the parabola intersects the y-axis. Now, when our parabola intersects the y-axis, that's where x is equal to 0, because that's right down the middle of our graph. So we need to find where x is equal to 0, and we're trying to find our y value right here. So if we go back to our let's grab our equation of our parabola from the previous problem. So we got a -5 fourths x minus 3 squared plus 4. And we are finding where it intersects the y-axis. So what we can do is just plug in x for 0 and then solve for y. Simple as that. So that'll leave us with -3 squared plus 4, -5 fourths. That will give us 9 times -5 fourths plus 4, which will be -45 fourths plus 4. And then we want to get that 4 on the right to have the same denominator, so we can expand it out into a fraction, which will be plus 16 fourths. And then we just simplify, leaving us with, I don't know why I'm doing double negatives there, but leaving us with -29 fourths. Oops, a little bit too fast. Any questions with that bit? All right, sweet. So if we have no more questions on quadratic functions, we are going to move on to polynomials and their graphs. Now, a polynomial is any function that can be written in the form of x values with some exponent and coefficients, where each exponent is a whole number and each of the coefficients are all real numbers. And when writing a polynomial, you can write them in standard form with them all expanded out, or you can write them in factored form, which is very helpful for finding zeros of polynomials, which we will cover later. And I guess like this is honestly a little bit messy. I guess to write something like as an example, a polynomial can be something along the lines of like 9x cubed plus 5x squared minus 3x plus 1. This would be an example of a polynomial. Pretty straightforward, pretty nice. So zeros of a polynomial are going to be values of x that can be plugged into our polynomial that will give us a zero, or that is a location where the graph of our polynomial will cross the x-axis. And if x minus c like is a factor of f, or I guess if our zeros is a factor of our polynomial, then 0 has to be a zero of our polynomial. And then if c is a zero, then x minus c must be a factor of f. If that's a little bit confusing, kind of is. Pretty much what that's saying is that if we have some sort of polynomial where it has the form of like x minus c, x minus b, x plus a like squared, if these are zeros, then they are factors of f, because this can be rewritten in standard form somewhere along the lines of like a x cubed and so on. And do keep in mind, this a and this a are not the same. They're just placeholders. But our polynomials can be written in either of those forms. And talking about this is that down here, when it's written in its factored form, those values of c and b and a, those zeros are factors of our polynomial. Sound good? Okay. Now, with multiplicity, that's pretty much just telling us how many zeros our polynomial actually has. And the number of our multiplicity also tells us the behavior of the graphs of our polynomials. For example, if we have a factor that is a multiplicity 1, our graph is really just going to look like a straight line, either going up or down, or even horizontal. That works too. If we had a graph with multiplicity 2, it's going to be a parabola, either going up or down. And then if we have a multiplicity 3 with our polynomial, it's going to have one end going down to infinity and the other end going up, or vice versa. Now, end behavior, that aligns a lot with our multiplicities, kind of like what I was talking about before. And the best way we can determine end behavior is by looking at the leading coefficient and whether there's a positive and negative in the front. And we take a look at the multiplicity of our polynomial. And that will tell us the general shape of it. So, for example, if we had a polynomial, negative a minus x squared, we can take a look at two things. We can take a look at if it is either positive or negative on our leading coefficient, which in this case it is negative. And then we can take a look at our multiplicity, which in our case, that is 2. With that, we know that it is going to be a parabola that both the right and left sides of its end behavior are going down because it is negative. And kind of continuing on with these different descriptions, I guess I kind of just explained it in my own words there. Does anyone have any questions on end behavior, how to determine it with bigger, more complex polynomials? We're all feeling pretty good on that? Yeah, we'll go through some examples, don't worry. Okay, so this question is asking us to choose the function from the following whose graph is shown. And just assume that A, B, C, and D are all positive real numbers. So there are a couple things that we can do to look at this graph to determine which of these functions it is. The first thing that we can do is we can look at all the locations where our graph touches or crosses the x-axis. So for example, right here and here are both places where our graph crosses the x-axis. And then here is where it touches. And we can use that information to help us determine which of these equations our graph is. The first thing that we can do is we can see where our function crosses the x-axis. If it crosses the x-axis, that means that our function is going to have an odd multiplicity at that 0. For example, these two pieces right here have odd multiplicity because it only has a power of 1 like in its exponent. It's like there's no 2 there. And because it's odd, that means it's going to cross the x-axis. And by looking at the inside of those factors, here we both have a plus, that means that the location or like the 0 of where that is going to cross is going to be on the left side of our y-axis, right? Because when dealing with graphs and like polynomials, if we have x, the inside of our polynomial is going to do the opposite of the sign, right? Like if we go plus b, it's actually going to be going to the left of our graph, b units, so on and so forth. So from here, we can see that in our actual graph over here, that the two places where our graph is going to cross the x-axis are going to be positive with our zeros. So f of x and h of x and t of x are all on the table for being correct, just because the insides of b and c have that plus sign. So we're going to keep on looking at those 3. The next thing we can do is take a look at the place where our graph touches the x-axis, not crosses. With this, we can take a look at the behavior of any even multiplicity. Here, let me erase that. It's a little messy. And as we can see here, both x minus d squared, both of these for the functions f and h have a negative in front of that d, which means it is going to be on the right side of our y-axis. So that's good. This one down here is a multiplicity of 3, which means it's going to cross the x-axis again instead of bounce off of it. And we're looking specifically for where it bounces, which means we need a multiplicity of 2. So we're from now on going to only look at either f of x or h of x. And the last thing that we can do is to determine which equation this is going to be, is we can determine the end behavior of our function. The way we do that is we look at what direction our function is going as we approach infinity. And as we can kind of see right here, they're both heading to negative infinity, which means that the leading coefficient of our equation is going to be a negative, just right there. So to wrap things up, I'm just going to do just really quick. We first want to determine the zeros, which in our case are our 2 crossing zeros are on the left side of the y-axis, right here. Our bouncing 0 is here on the right side of the y-axis, and then our end behavior is negative, which means we are heading to negative infinity as we approach infinity, and our multiplicity is even, so they're both heading in the same direction. Sweet. And so our solution is going to be that h of x right there. Any questions with that one? We're all feeling pretty good about this one. All right. Now let's do another practice problem with this, and we pretty much we want to do the same things as we did before. So let's first find our zeros and determine whether they're negative or positive. So we have a zero multiplicity 2 right here. That is, it is going to be negative. Let me just. It's going to be negative. We have a 0 that crosses the x-axis, which is going to be positive, and then another one that bounces that is positive as well. So if we have any negative zeros, that is going to be on the inside of on our 0, it's going to have a plus sign. And since it's going to be bouncing, it's going to have a multiplicity of 2. So that means this one works and this one works because we have a positive on the inside of that 0 and it is squared. Sweet. Then we need to find a 0 that crosses the x-axis or has an odd multiplicity. And since it's crossing the x-axis on the right side of it's going to be positive, so we're going to have instead a negative on the inside. So this works and this works. So let's keep on rolling with either of those. Last thing is that we have another bouncing 0. So both of these work. And then we can determine the multiplicity of our entire equation. What we can do is we can just multiply all of our multiplicities together. So here we have 2, 2, and 1. That will give us a multiplicity of 5 because we just add those together. 2 plus 1 plus 2 is 5. Same thing down here. We have a 2, a 1, and a 2, giving us 5 as well. Both of those are odd, which means that we are going to have one endpoint going to negative infinity and one point going to positive infinity. And then last thing we can do is determine our end behavior, which as we head to the negative infinity, we go negative. As we head to positive infinity, we go positive. And so that means there's not going to be a negative in front, which down here, there's not one. So the correct answer for this problem is going to be our T of X. Any questions with how I determined where the zeros were, the multiplicity of our equation, or how I determined the end behavior of our function? All good? All right, well, let's keep on going. Polynomial division is going to be the next thing that we're going to be working on. And this also includes synthetic division, and we can do practices with both. So polynomial division is a lot like long division, but we are dividing two polynomials instead. It's a really good way of simplifying polynomials so that we can work with them easier. And it's a really good way of turning a standard form polynomial into its factored form. So for example, if we have this polynomial, the 2x cubed minus 6x squared plus 1, we can divide it by x squared plus 2, and then that will give us, that'll either lead, and that will lead to a factored form of the polynomial plus its remainder. So the way how we set this up is we set it up just like we would with long division. We have 2x cubed minus 6x squared plus 1 on the inside and the x squared plus 2 on the outside. And the way how we do this is all we want to look at is this first term on the piece that we are dividing by. And we want to see what we can multiply this by to get this term inside of our division. So for us, what do we need to, the thing that we want to multiply x squared by to get 2x cubed, in this case, would be 2x. Because if we multiply 2x by x squared, we get 2x cubed, which is what we are looking for inside of here. And so we then multiply the 2x cubed by both of these pieces, and we bring it down here and subtract it. So we get negative 2x cubed plus 4x, And since we have that negative that we're distributing, we're going to be subtracting that from all the pieces underneath the division. So as we perform that, that subtraction, we're going to get 0 minus 6x squared minus 4x plus 1. And with that, and that 6x squared, that just came from this piece coming down. Same with the plus 1. And since our original polynomial didn't have any just x values in it, as you can see, it just has the 6x squared. There's no just x. And so we just bring down that negative 4x from the previous piece right down into the next step of our division. Sound good? All right, from here we just keep on going. So now, for us to get negative 6x squared, we want to multiply our piece that we're dividing by, the x squared plus 2, by negative 6. So we, up at the top of our division, we put our negative 6, and then we just perform that multiplication and bring it down. So we would get negative 6x squared minus 12, and then we perform that subtraction. And reminder, I'm performing this multiplication and putting it inside parentheses just to make sure that our signs are correct. Because if we mess up the signs, it can throw off our entire division. So just keep that in mind. So with this, as we reverse those signs, I'll reverse them right here. Oh, this eraser is huge. If we reverse those signs, we would get 6x squared plus 12 instead. And so if we perform that, the 6x squared plus the negative 6x squared is going to cancel, and we will get just negative 4x plus 13. And the last thing is that if we can no longer divide x squared plus 2 into our negative 4x plus 13, that is just going to be our remainder. And we put that at the end in the form of the negative 4x plus 13 over x squared plus 2. And we're just going to put that at the end. So to finish off our division, it is going to look like 2x minus 6 plus negative 4 plus 13 over x squared plus 2. Now, for the solution in this, they have it structured. Go back. There we go. They have it structured a little differently, where they have a negative in front. They have a negative right here, and these signs are switched. That's just the simplest way that I can explain that is that they just change which signs go where. So if I were to multiply this entire thing like this, I guess, yeah, the best way to describe this is this negative gets pulled out front, and that means I have to change the sign on the negative 13 as well. So we can rewrite this. It's equivalent, and we can just rewrite this to be negative 4x minus 13. And that's the same thing. And this is the solution to our polynomial division. Any questions on that? Or are we feeling pretty good on that? Feel pretty good? Okay. We are starting to run a little low on time, but I did say that we can do a quick bit of synthetic division practice. Now, synthetic division is just another way of performing polynomial division. However, you can only perform synthetic division when you are dividing by a zero that has this form. So for this question, it wouldn't work since our zero since the thing we were dividing by was in the form x squared plus 2. For synthetic division, it has to be in the form of just x minus 1, x plus 3. Just there can't be like an x squared. So, let's see here. see if I can come up with a good example on the spot. Let's do x minus 3 dividing 2x squared plus 6x plus 1. And we're going to perform that with synthetic division. So the way how we do this is with synthetic division, you take the 0 that would be in here, which in our case, our 0 would be x equals 3, because if we plug in 3 as our x, we will get 0. We take this and we construct a synthetic division table. And all you do is you put the coefficients of our polynomial up here into columns right here. And then there's a couple of tricks that we can do to perform this, and this will tell us, and it's a shortcut to performing polynomial division. So what we do to start off is we just take this first coefficient and bring it straight down. We don't touch it, we just bring it straight down. The next thing you do is you multiply 3 by this and put it under here. Then you add going down and you put the result down here. And then the last thing and then same thing as before, you multiply 3 by 12 and you put it underneath here, which in this case would be 36. You add down, and then that last bit is going to be our remainder. Now, this is a terrible example because I should have put at the front of this 6x a negative 6x. So I'm going to quickly rewrite this to be negative 6, just because that'll make our math a lot cleaner and easier, and it'll be easier for me to explain. So if our polynomial was in the form of 2x squared minus 6x plus 1, we would get same thing as before. 3 times 2 is 6, and as you add them down, you get a 0. Sweet. And then if you multiply 3 times 0, this bit is going to be a 0. You add that down, you get a 1. Stop. And with this, these pieces down to the bottom, this tells you pretty much what is going to be the coefficients for your division, which for this last piece is our remainder, so we don't include that. And so these last two pieces are going to be, this is going to be the x, and this is our constant. So our 2x minus 6x plus 1 over x minus 3 is equal to 2x plus 1 over x minus 3, since that is our remainder. And since this is a 0, we don't include that. And that's a quick little crash course in synthetic division. The thing is, we would get this exact same answer if we did it with normal polynomial division. This is just a quick little shortcut to get there if you don't want to perform normal polynomial division. I would personally recommend to just go with polynomial division, just because it'll give you the correct answer, and it's also, in my opinion, it's just a little bit cleaner and easier to follow. The synthetic division is nice though, if you're comfortable with it and if you have used it before. So now, so let's keep on going to real zeros of polynomials, because we're getting close to running out of time and we have quite a couple more topics to cover. Now, rational zeros are, so the rational zero theorem is a tool for us to be able to find zeros of our polynomials. And the way how we do that is when we are given some polynomial, in this case this, all of the possible zeros that we can have for this will be in the form of P, will be in the form of PQ. Let me erase that. Where P is a factor of the constant at the end, and Q is a factor of our leading coefficient. And what I mean by that is that P can be, in our example down here, P can be 1, because the only factor of 1 is 1. And our Q can be either, well, I should say, P can be positive or negative 1. It can be either. And our Q can be positive or negative 2 or 1, because the factors of 2 can be either 2 or 1. So all the possible zeros for our polynomial 2x cubed minus x squared minus 2x plus 1 can be positive 1, negative 1, positive 1/2, or negative 1/2. Those are all of our possible zeros. So what we can do is we can test those zeros, and from there, we can then, after finding one of them, find the rest either by using polynomial division, synthetic division, or other values like the quadratic formula to find the rest. So let's do that quickly with this one right here. And let's test positive 1 as one of our zeros. So what we can do is we test it by and remember, if our root is positive 1, the 0 for it is going to have x minus 1 so that x equals 0 so that our 0 equals 0. That's the best way to describe it. So we do this and we perform that polynomial division with the 2x cubed minus x squared minus 2x plus 1, just like that. Then we just go through and perform polynomial division like normal. This will get us 2x squared. We multiply the 2x squared by that x, get negative x cubed. In this case, it's going to be plus 2x squared. Perform that subtraction, we will get x squared minus 2x plus 1. The way how we get that is by multiplying it by x, giving us x squared minus x. We perform that subtraction, that's going to give us, I'm running out of room. Let's see here, that's going to be a positive because we are subtracting it. That'll give us negative x plus 1. And the way how we get that is by multiplying it by negative 1. Because that'll give us positive x minus 1, leaving us with 2x squared plus x minus 1, just like that. From here, so we've already found one of our zeros, which is that x equals 1 right there. And this is what we got since our remainder is 0. Sweet. So we performed our polynomial division and we got a whole polynomial from it with no remainders. Super nice. So what we can do is we can then test one of our other zeros and go from there. One thing I can kind of see is that there's a 2 in front of our x squared in front of all of this. So what we can actually do is we can factor out that 2 and pretty much just divide our entire polynomial by 1/2. And it will pretty much, we're just going to rewrite this to be x squared plus 1/2 x minus 1/2. It's the same polynomial. It's just written, we've just divided everything by 2 so that we can easily find this by finding its, what is it called? Finding its square? I think that's what it's called.
Completing the square.
Completing the square. I was really close to it. So we can complete the square from this by seeing that x that if we factor this, we're not completing the square with this, we're just factoring it. If we factor this into its 2 factors, we can see that we can split it up into x plus 1 and x minus 1/2. Because, I don't know, because I don't know, the best way I can describe it is you factor into those 2 pieces, and those are our last 2 roots. Those are our last 2 zeros. And so I would stop drawing over where the zeros are. There we are. So our 3 zeros for this polynomial are going to be 1, negative 1, and 1/2. And the reason why we know there are going to be 3 zeros is because the greatest multiplicity of our polynomial is 3. And that can tell us how many zeros we are going to have for the whole polynomial. So super nice. Does anyone have any questions with that? Yes.
Would you be able to just plug in 2x squared plus x minus 1 into the quadratic formula and get the same answer?
So would we be able to plug in this piece right here into the quadratic formula? Yes, you could.
Okay.
And that would also give you the correct answer. Yes.
How did you find the list of potential rational zeros?
So to find the list of potential rational zeros, the way how we do that is we use the rational zeros theorem from, if it will go back, from before, where all of the possible rational zeros are in the form P, Q, where P and Q are going to be the positive and negative factors of our constant at the end and the leading coefficient at the front. So, for example, if, I don't know why, sweet, blank slide. So let's say we have a polynomial of like 9x squared, x cubed, some values in the middle, plus 3. To find all the rational possible zeros that could be for this polynomial, we take P, which is all of the possible factors for our constant at the end. So that's going to be all positive and negative values of factors of 3, which in our case is just going to be 3 and 1, because nothing else can really divide into 3. And we put that over Q, which Q are all the positive and negative factors of the leading coefficient at the front, which in our case is 9. So anything that can divide into 9, which will be 9, 3, and 1. So all the possible zeros are all of these combinations. So our possible zeros for this will be positive and negative, 1, 1/3, and 1/9. And the reason why there isn't a 3/9 in there is because 3/9 is the same thing as 1/3. So we don't need to repeat it. Does that answer your question? Yeah? Did you have a question? No? Okay. So that is how we find all the possible zeros for, well, I guess I missed one. There should be a 3 here as well, because 3 over 1 is just 3. I missed that one. But those are all the possible zeros for this polynomial. And then you can use those and test them with our polynomial division like we did before. And that's how you can find all the zeros for this polynomial, which in this case, there would be 3. Okay, let's keep on going. Yeah. Take one.
Hey,
You got this.
awesome sauce. Okay, so we're gonna talk about something very near and dear to my heart because I had to prove it last semester in one of my classes, the fundamental theorem of algebra. Okay, so the fundamental theorem of algebra tells us if we have a function that is a polynomial with real number coefficients and a leading term of a sub n x to the n, then f of x can be written in the form f of x is equal to a sub n. So we pull out that leading coefficient to the front, and then in complete factored form, where the c1, c2, cn are complex numbers, and these complex numbers are not necessarily unique. Remember, complex numbers are of the form a plus bi. So if if b is equal to 0, then we just have a real number, which can either be rational or irrational. Okay, so, and when it says not necessarily unique here, that just means we can have something like x minus 1, and that's technically x minus 1 squared. But if we factor it fully out into this, they're just not going to be unique. Okay, okay. So polynomials of degree n have precisely n factors of the form x minus c. That's why we have c1, c2, all the way up to cn. And we have x to the n right there. So we can completely factor every polynomial, okay? So every polynomial can be completely factored into complex numbers. This is always going to be true. If you are just in the rational numbers or just in the real numbers, that's not always true. Once you get in the complex numbers, this is always true. And then the sum of all multiplicities of all the zeros of a polynomial is equal to the degree, okay? So up here, let's say we have x minus 1, x minus 1, x minus 2, x minus 3. We see that this is eventually going to multiply out because we multiply x by x by x by x. So we're going to get the highest degree of x to the fourth. And so we have x to the fourth plus da 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 da. And we see we have x to the 1, x to the 1, x to the 1, x to the 1. So we have x1, 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 1 plus 1 plus 1 plus 1 is equal to 4. Okay? So that's always going to be true, even if we write it like this instead. These two still have multiplicity 1. This one has multiplicity 2. 2 plus 1 plus 1 is 4. Okay? Okay. So, any questions on this? Okay. This is helpful for questions that are like, do we have any imaginary roots? Because if we have x to the n equation and we find, let's say, n minus 1 real factors, or x minus, let's say n minus 2 real factors, then that means that there's 2 imaginary factors. Okay. Okay. Okay, so let's look at part 1. Okay, so we use the graph to determine how many rational zeros there are for the function f of x is equal to x to the 5th minus 2x to the 4th minus 8x to the cube plus 16x squared plus 7x minus 14. Okay, so this is asking about rational zeros, not real zeros. So what we want to do is use the rational zeros theorem that we talked about earlier. So we have our coefficient for the leading coefficient is 1. And our constant coefficient is negative 14. Okay, so all the factors of 14 or negative 14 is going to be plus or minus 14, plus or minus 1, plus or minus 7, and plus or minus 2. And then all of the factors for Q are going to be plus or minus 1. Plus or minus 1 are the only ones that divide 1. Okay, so our possible rational roots that we can have are plus or minus 14, plus or minus 1, plus or minus 7, plus or minus 2. Because if we divide all these by plus or minus 1, we're just going to get that same list again. Okay? Okay. So now we just want to go about plugging it in. I usually like to start with the lowest positive one. So we have positive 1 right here. So we have 1 minus 2 minus 8 plus 16 minus 7 minus 14. Okay, well that's 16 gets rid of 14 and 2. And then we have 1 minus 8 minus 7, which is very clearly negative and not 0. So it's not 1. Okay, let's try negative 1. If we plug negative 1 in, negative 1 raised to the 5th, raised to an odd power is still negative 1. So we have negative 1 minus 2, because x to the 4th gives us positive 1. And we still have the negative 2. And then we have plus 8, because x to the 3rd, x cubed for negative 1 is negative 1. Plus 16, minus 7, minus 14. Okay. So we still have this 16 cancels out the 2 and the negative 14. Then we have negative 1 plus 8 minus 7. Yay! Okay, so negative 1 works because that gives us 0. Okay. Okay, so we can factor it out using, I don't know how much of this she wants me to do. We have x plus 1 for x minus 1. We can use polynomial division. X 5th minus 2x to the 4th minus 8x cubed plus 16x squared plus 7x minus 14. Okay. So x to the 5th, x plus 1 fits in x to the 4th times. Sorry, I'm running over the text a little. Plus x to the 4th. So that turns it to negatives. So those cancel out. Then we have negative 2x to the 4th minus x to the 4th, so negative 3x to the 4th. And then we have negative 3x3 goes into that. So we have negative 3x to the fourth minus 3x to the 3. And that gives us, let's see, that's going to cancel out. So we have positive 3x to the 3 minus 8x to the 3. So we have negative 5x to the 3 plus 16x squared plus 7x minus 14. Okay, and then we have negative 5x squared, negative 5x squared, or x cubed, minus 5x squared. That turns into a positive, so we have 21x squared plus 7x minus 14. Then we have plus 21x, so we have 21x squared plus 21x minus 14. Okay, and then those go negative, so we have that 7x minus 21x gives us negative 14x minus 14. So you have minus 14, awesome. And then we have minus 14x minus 14 gives us 0. So you don't have a remainder. So awesome, that is a root. We checked it, we double checked it using polynomial division. That gives us the root. Okay. I'm not gonna go through and, oh, I guess we can check the, check the graph. Okay, so we have x plus 1, x to the fourth minus 3x cubed minus 5x squared plus 21x minus 14. Okay, awesome. Okay, so we can now check on the graph. We see that negative 1 is one of them. And it looks like 2 is one of them. Okay, awesome. Oh, maybe 1 is one of them. Maybe I did math wrong. Okay, but anyways, negative 1 was one of them. Okay, awesome. Whoa. Ryan, do you know how to get that off the screen?
On the left, the press dismiss.
Oh, okay.
Keep them popping.
Okay, thank you. Okay, so what we found is we have 3 rational zeros because we check up here, we check that we have plus or minus 1 on both of these, and we have positive 2, but we see that there's no negative 14, no positive 14, no negative 2, no plus or minus 7 on here. Okay. Okay, so that is very helpful for us. We can usually just check these numbers and then just look at the graph instead of doing the complete rational root test for all of them, or rational zeros theorem for all of them. Okay, so what we found is that out of our 5 possible roots, remember there has to be 5 possible roots from the fundamental theorem of algebra. Out of our 5 possible roots, we know 3 of them are rational. Okay, so if we want to determine how many irrational zeros there are, we already found that there's 3 rational ones. Okay. That means that these other 2 roots where this passes through have to be irrational. Okay. So there are 2 irrational roots. Irrational roots does not mean they are not real. It just means that we can't get them in fraction form. Like the square root of 2, we can't get that in fraction form. Okay. Okay. So that means now if we're checking how many imaginary zeros we have, this is the same function. It tells us that any zero is not rational or irrational must be imaginary. What we found is we have 3 rational and 2 irrational. Well, we already know that there's supposed to be 5 roots. It factors into 5 linear factors, and 3 plus 2 is 5, so that means we can't have any imaginary zeros. Okay, so there are no imaginary roots. Okay, any questions on this? Yes.
So if the graph like only had 4 zeros that was shown, then would there be 1 imaginary?
Technically, yes, but you just have to remember that imaginaries come in pairs. So there would have to be
Okay.
another imaginary number, but yes. If it had only 3 zeros going through the graph, and that means 2 would have to be imaginary.
Okay.
Yep.
How would you spot a zero on the graph?
Just whatever passes through the x-axis. So right along here. So these are rational because we found out they plus or minus 1 and positive 2 works. But the other two we couldn't find because they weren't part of our list up here of rational roots. So that means that they're irrational because they still go through the x-axis at a real number, which makes them not imaginary, but they're not rational, so they're irrational.
Mhm.
Okay, any other questions on this? Okay. Awesome sauce. Okay. So now we want to find all the zeros of this polynomial. Okay. Hint, one of the zeros is the square root of 2i. Okay, that makes this a lot easier on us because what did I just say?
Imaginary zeros come in pairs.
Yes, exactly. Imaginary zeros come in pairs. So if one of the values is square root of 2i, that means another one of the values is this negative square root of 2i. Okay, so that means we have x plus square root of 2i and x minus the square root of 2i that are already factors that we've discovered. Okay, so what we can do now, instead of doing 3 rounds of polynomial division, we can instead simplify it to 2, because we can multiply these two factors together to get x squared plus square root of 2ix minus square root of 2ix, which cancels out, and then we have plus square root of 2i, negative square root of 2i, which gives us 2i squared, or negative 2i, but we still have this negative right here. That changes to a positive, so we have x squared plus 4. Wait, that I is not supposed to be there. Not, oh my gosh, not 4, 2. I keep squaring it in my head. Okay, x squared plus 2. Okay. Okay, so we have a confirmed factor of x squared plus 2. Now we want to find our other ax squared plus bx plus c, because we have x to the 4th, so we know that there has to be another quadratic factor that we can pull out. Okay. Okay, so we can now use polynomial division. So we have x squared plus 2. And we have x to the 4th minus 4x cubed minus 3x squared minus 8x minus 10. X squared times x squared equals x4. So we have x to the 4th plus 2x squared. Okay, that cancels out. Remember we have the negative 4x cubed still there. Then we have negative 3x squared minus 2x squared. So we have negative 5x squared minus 8x minus 10. So now we have negative 4 x. So we have negative 4x cubed minus 8x. Awesome. That gets rid of this one, and it also gets rid of this one right here. So now we have negative 5x squared minus 10 left. So that gives us negative 5 up there. So we have negative 5x squared minus 10, which gives us 0. Awesome. So now what we have is x squared plus 2, and we have x squared minus 4x minus 5. Okay, now we want to find two numbers. Two numbers that add to negative 4 and multiply to negative 5. And that we can see is negative 5 plus 1. Okay, so what this does is it factors to x squared plus 2, x minus 5, x plus 1. So that's that factored. If you want to factor it further, you can again bring in this part. Okay. Okay. Awesome. Any questions on this?
Just to make sure,
Mhm.
our answer for this one would be +5, -1, and then the x plus square root of 2i. And
Yeah, the plus or minus square root of 2i. Yeah. Mhm. Yeah. Yep. So we have two real rational, because -5 and +1 are rational. Two real rational roots, and we have two imaginary roots. Okay. And those add up to 4, which is exactly what we want, x to the 4th. Okay. Okay, moving on to rational functions, function graphs. Okay, so a rational function is any function where the output can be defined by dividing a polynomial by a polynomial. So if we have, let's say, two quadratic equations, we have x squared plus bx plus c over dx squared plus ex plus f. That's going to be a rational function. Okay. And then it can be any polynomial, just it doesn't have to be quadratic, but a quadratic is a polynomial. So, okay. So they're a fraction where the numerator and the denominator are both polynomials. Okay. Okay. So important things to know about rational functions, especially when it comes to graphing them, is we want to understand what holes are. Rational functions have holes for any input that is a 0 of both the numerator and the denominator. So they divide to 1 for every x value besides that one. So if, for example, let's say we had let's say we factored the numerator and denominator, and we get x minus 1, x minus 2, x minus 3, x minus 2. This is in both the numerator and the denominator. You can divide it out, then you would just be left with this. But you still have to remember that this was causing a problem in your denominator. Okay? This x equals 2, at some point at x equals 2, we're having a problem in our denominator. Okay? So we can divide it out so it doesn't make it a vertical asymptote, but it makes it a hole still. That means it's not defined at 2, x equals 2. Okay? So yeah, we find holes by finding common factors of top and bottom and find the x coordinate and using the reduced form to find the y coordinate. Okay? So again, we divide it out. So if we have x equals 2, we can plug that back in over here. 2 minus 1, 2 minus 3 is equal to 1 over -1. So this is going to be at 2. This is going to be at 2, -1. That's where the hole is going to be. Okay. So you put the y coordinate, you put the x coordinate in the reduced form in order to find the y coordinate. Okay. Okay. Awesome. Okay, vertical asymptotes, we find them by finding the zeros of the denominator of the reduced rational function. So when the denominator is equal to 0, the function is undefined. Remember, we have the problem of if we have a number divided by 0, that's undefined. Same for rational functions, so we have to worry about it when that might occur. Graphically, it appears the function goes to a positive or negative infinity. So either of those, as the x values approach the asymptote. And it will get close, but it will never cross the line. Okay. With horizontal asymptotes, you can cross the line. It's just saying that it will eventually steady at that number, or be close to steady at that number. With vertical asymptotes, you do not cross the asymptote. Okay. Okay. Awesome. So over here, we have, in our reduced form, we have x minus 1 over x minus 3. X minus 3 is not a hole, but a vertical asymptote, because in the denominator, it causes a problem, but we can't cancel it out. Okay, so that's going to be a vertical asymptote, while x minus 2 would be a hole. Okay. Any questions on holes and vertical asymptotes? Okay. Okay, so end behavior. End behavior is when horizontal asymptotes come in. So if the degree in the numerator is less than the degree in the denominator, so for example, if we had x to the squared, x to the cubed, then the horizontal asymptote is at y equals 0. Okay, that's always true. Okay. And this can change to the 4th or to the 5th or to the 6th. It can be any amount higher than the numerator. It just has to be higher than the numerator for this to be y equals 0. If the degree in the numerator is equal to the degree in the denominator, then the horizontal asymptote is found by dividing the leading coefficients. So up here, if we had x squared over x squared, and they're both da 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 da, then their leading coefficients would just be 1 over 1. So we would have a horizontal asymptote at y is equal to 1. Okay. If it was like 5 over 2, we would have a horizontal asymptote at y equals 5 over 2. Okay. And the end behavior is an oblique slant asymptote if the degree in the numerator is exactly 1 greater than the degree in the denominator. Okay, so up here I said it could be any number, the denominator could be any degree higher to still have the horizontal asymptote at y equals 0. For this one, it has to be exactly 1 greater for us to have an oblique asymptote in the numerator. So it'd have to be like x3 over x squared. Okay. And we can find the slant asymptote by dividing the numerator by the denominator, and we just ignore the remainder. The remainder will usually, it will be some constant over x plus another constant. And as we go to infinity, this gets larger and larger and larger and larger and larger and larger and larger until the numerator is so inconsequential that it basically is 0. Okay? Okay. So that's why we can ignore the remainder. So we just divide the numerator by the denominator, ignore the remainder. That tells us the equation that our line will eventually converge to, our curve will eventually converge to, I should say. Any questions on this? Okay. Zeros. Rational functions have zeros when the numerator has a 0. Okay. But the denominator does not have a 0. Remember, technically, we can have our 0. We can have a 0 that is both in the numerator and denominator, but there would be a hole at the 0. So technically, it's not 0. Okay. Okay. This is true because 0 divided by anything is just 0. Okay. So whenever our numerator is 0, it's going to be 0. It doesn't matter what the denominator is. Okay. So let's look at some examples really quick. This question is, does the following function contain any holes? And if so, what are the coordinates for the holes? Okay, so what we want to do is we just want to factor it. Okay, so we want something that adds to 1 and multiplies to -2. This is going to be 2 minus 1. 2 minus 1 is 1, 2 times -1 is -2. So this factors into x plus 2, x minus 1. And then we want something that adds to -3 and multiplies to 2. So if we have -2 plus -1, that's -3, and -2 times -1 is +2. So we have x minus 2 over x minus 1. Okay, awesome. We can automatically see what that hole is. It's going to be x minus 1 over x minus 1 can cancel out. Okay? So our hole is going to be at x is equal to 1. Okay, awesome. So now we have our reduced form. We have x plus 2 over x minus 2. Well. Okay. And we want to see where the y coordinate is for this hole. So we plug x equals 1 in. So we have 1 plus 2 over 1 minus 2. So we have 3 over -1. So we have -3. Okay. So that means our hole is at 1, -3. Any questions on this? Okay. Awesome. Okay. And then we want to consider the graph of the following function. So we want to look if this has any vertical asymptotes. Okay. So the denominator we can pull out at 2x. So we have 2x, x minus 2. Okay. And then the top we can pull out a 5. So we have 5x squared plus x minus 6. And then we want something that adds to 1 and multiplies to -6. So that's going to be -2 plus 3. So we have 5x minus 2, x plus 3. Okay, awesome. So we see that our whole cancels out. So we have a whole at x equals 2, and that still leaves 2x. So that means that we'll have an undefined problem at x is equal to 0. So we have a vertical asymptote at x equals 0. Any questions on this?
When would it be anything else? The vertical asymptote.
Oh, if we didn't have, like, for example, if we didn't have the x minus 2 up here, then x equals 2 would be a vertical asymptote. But because they canceled out, then we just have the 2x in the numerator, in the denominator, which means when x equals 0, we have 2 times 0 is equal to 0, so we have a number over 0, which is undefined. Okay. Okay, awesome. Does the graph have any vertical or horizontal asymptotes? Okay. Well, we see that the degrees of both sides are the same. They're both 2. So that means, according to our beginning slide that we had, we take the ratio of the leading coefficients. So 5/2. So we have a horizontal asymptote at 5/2. Oh, not that one. Yeah. Okay, at 5/2. Okay. Okay. And then where does the graph cross the x-axis? This is just asking us where the zeros are. So we have 5 x minus 2 x plus 3 as our numerator. So that means it will cross the x-axis at x equals 2, x equals -3. Or it will cross the x-axis as x equals 3, sorry. -3, because this cancels out with the denominator. Okay, oh, and then it wants us to write it in point form. It's a 0, so it's just y is 0. Okay? Yes,
And that -2 is because we had
the whole, yeah, yeah, exactly. So we don't want that one. Okay, awesome. Okay. So now right here, we're just graphing what we learned. So we know that we have a horizontal asymptote at y equals 5/2. So right here, we're gonna have a horizontal asymptote. And then we have a vertical asymptote at x equals 0. Right there. We have a 0 at x is equal to -3. And we have a hole at, what was it? Oh, I guess I didn't plug it in. That's fine. It doesn't want us to graph it anyway. Okay. So this is gonna end up looking something like, yeah. And then we don't have another 0, so it's gonna be something like that. Okay. Okay, awesome. Okay, so okay, we're gonna run through these last ones really quick. Does the graph have any vertical asymptotes? This factors to x plus 2, x minus 1 over, let's see, we can pull a 2 out, x cubed, oh wait, 2x out, x squared plus 2x minus 3. So you have 2x X minus 1, x plus 3. Okay, so x minus 1 is a whole, so that means we just have a vertical asymptote at x plus 2, or x equals -2. Okay. And then we have an oblique asymptote because our degree of the numerator is only 1 bigger than the degree of the denominator. So that means we can divide x squared plus x minus 2 into our numerator. So we can multiply that by 2x. So we have 2x cubed plus 2x squared minus 4x. So we end up with 2x squared minus 2x. But again, this is our remainder, which we ignore. So we just have 2x. So we have y is equal to 2x, like this. Our graph is going to eventually converge to. So if we kept going on to infinity, okay? Okay. Or 2x plus 2, yeah. Okay. So, and we don't usually have to worry about the constants. Okay. Awesome. And then where does the graph cross the x-axis? This is just asking us, we have 2x, x minus, what was it? X minus 1, x plus 3. Remember, x minus 1 is a whole, so we just have 2 zeros at x is equal to 0 and x is equal to -3. Okay. Okay, awesome. And then it just wants us to plot our asymptotes down here. So we are going to have our oblique asymptote right there. And then we have a vertical asymptote at, what was it? X equals -2. And then we had a 0 at x equals 0 and -3. Right? Yeah. Okay. So that means it's gonna do something a little bit crazy wonky. Should be. Okay. Okay, awesome. Okay, any questions? Sorry, we had to rush through the last bit, but there's another CBE that needs to happen. Review. Any questions before you go? Okay, awesome. Remember we have the if you want to find more resources, you visit usu.edu/math/amlec for more videos, resources, tutoring times, and recitation later office hours. They also have all the CBE review times listed if you want to look on there for upcoming CBE reviews, what time they'll be. And yeah, thanks for coming.